It's my pleasure to introduce Marc Lackenby, who has been my colleague for 13 years, and during these years he has won the Whitehead Prize from the LMS. He has been an advanced fellow of the EPSSC and won a Leverhulme Research Prize. Just 2 years ago, he also spoke at the ICM in Hyderabad. So today he will talk about Dehn fillings.
Great, well, thank you very much indeed. It's a great pleasure to be here. It's been a great conference so far, and I'd also like to say how pleased I am that the Clay Maths Institute is coming to Oxford. I hope it's the start of a long and fruitful relationship between the two institutions. So I'm going to be talking about a resolution of an oldish problem in three-manifold theory on the topic of Dehn surgery. So what is Dehn surgery? Well, Dehn surgery is a method of building three manifolds, which was invented by Dehn, obviously, and what you do is you start with a knot or link K in the three-sphere, and you drill it out. So you remove an open regular neighborhood of K, creating a three-manifold M with boundary. And that boundary is a collection of tori, one for each component of the knot or link. So you've removed a collection of solid tori from the three-sphere, and then you glue them back in. You reattach those solid tori to the manifold M, but in a different way. Okay, so what we do is we reattach solid tori to this manifold M in a different way from the way they were removed. So the resulting manifold that you create is obtained by Dehn surgery on K. So what are the different ways of attaching these solid tori? Well, the essentially different ways of reattaching the solid tori are parameterized by so-called slopes on the boundary of the neighborhood of K. So what exactly happens? Well, you have each solid torus that you reattach has a little meridian disk, and the boundary of that meridian disk is a simple closed curve on the boundary of that solid torus. But that boundary is getting glued onto the boundary of the neighborhood of K. And the boundary of the meridian disk will then become a simple closed curve on this torus. And curves on the torus are specified just by two numbers, P and Q, saying how many times the curve winds P times round one way, round the meridian, and Q times round the other. So the set of ways of reattaching the solid torus are specified by a pair of coprime integers, P and Q. So one actually normally puts P over Q, realizing it as a fraction union infinity, or possibly infinity. So the set of it turns out that where you send the meridian of the solid torus completely determines the manifold that you get. So the ways of reattaching are parameterized by the set of isotopy classes of essential simple closed curves on these tori, the one for each component of the link. So an isotopy class of essential simple closed curves is called a slope. Okay, so surgery is a very nice way of building three manifolds, and there are a number of reasons for this. One reason is that it's a sort of a universal construction. So there's an old theorem of Lickorish and Wallace that any closed orientable three manifold is obtained by surgery on a link in the three-sphere. You can then ask, so that's a sort of existence. How about uniqueness? Given the three manifold, how many different ways can it be constructed by surgery on links? And again, to some extent the answer to that is known. So there's a theorem of Kirby that says that any two surgery descriptions of a three-manifold differ by a sequence of so what are now called Kirby moves. So this is a picture plundered from his paper. On the left here is a diagram of a link with three components, and on the right there's a diagram of a different link, but they specify the same manifold that when you perform certain surgery along them, and they differ by just one of these Kirby moves, the sort of the key Kirby move, which involves sliding one component of the link over another. Okay, so why is surgery a nice way of building three manifolds? The reason is that you can see often many properties of the three manifold coming from properties of the knot or link. So for me, and for many people, that's one of the reasons why surgery is an attractive construction, that you can see three-dimensional properties of the manifold as properties of the knot or link. And I'll make that statement more precise in a bit. There's a generalization of Dehn surgery called Dehn filling. Here you start with not necessarily a knot or link, but you just start with an arbitrary compact orientable three-manifold M, and with the property that its boundary is a collection of tori. You pick a collection of slopes S1 up to Sn on the boundary, one on each boundary component, and then you glue in solid tori onto those boundary components so that the meridians are attached onto these slopes. And the resulting manifold is called MS1 up to Sn. And it's obtained from N by Dehn filling. As I say, there's a general theme in surgery theory that properties of the unfilled manifold, M, manifold that you start with, should be inherited by properties of the filled-in manifold, M, S1 up to Sn, for generic slopes S1 up to Sn. So that's the general theme, and that's what the Dehn surgery problem is about. So the Dehn surgery problem deals with specifically the geometry of these manifolds. So there was as everyone knows, there was a major revolution in three-manifold theory, first of all in the late 70s and early 80s, when Thurston introduced his geometrisation conjecture and proved some of it, and when the full conjecture was proved by Perelman about 10 years ago now. So the geometrisation conjecture, I'm not going to state precisely. It, roughly speaking, says that any closed orientable three-manifold has a canonical decomposition into geometric pieces. And there are 8 sorts of geometries that you use, and by far the most important of these is hyperbolic geometry. So an even looser way of phrasing the geometrisation conjecture is that almost every three-manifold is hyperbolic. So just to remind you, we've already seen some hyperbolic geometry in the conference, but just here's a brief refresher. So a manifold's hyperbolic if, when you remove its boundary, you can express that open manifold, possibly open manifold, as the quotient of hyperbolic 3 space by a group gamma acting, it's a group of isometries acting discretely and freely. Here's some examples. So take here's the Seifert-Weber dodecahedral space, which is a dodecahedron with opposite faces glued with a twist, which you can see there. Here's another picture I plundered off Wikipedia. So it turns out that you can realize this dodecahedron as a hyperbolic dodecahedron, and if you choose it in the right way, then these gluing maps are isometries, and you can arrange that the angles around each edge that you create add up to 2 pi, And so by Poincaré's polyhedron theorem, you create a hyperbolic structure on your manifold. So the manifold is just a single polyhedron with face identifications. That single polyhedron, its inverse image in hyperbolic space, is a whole tessellation of hyperbolic space by dodecahedra. Here's a famous picture of that seen from the inside of hyperbolic 3 space. Here's a whole load of hyperbolic dodecahedra all tessellating it. If you look carefully, you can see various bits of dodecahedra around the place. Okay, so this is a hyperbolic structure, and there's one other particular hyperbolic manifold that I want to focus on, which was studied in detail by Thurston, and that's the complement of the figure-8 knot. So here's the figure-8 knot, and it was, I think, Riley who was the first to impose a hyperbolic structure on its complement. And this was also studied by Thurston, and the way that Thurston described it is as follows. So here's a really amazing fact, which is completely not obvious, that the complement of this knot is homeomorphic to this space here. So this space is 2 tetrahedra with various identifications. So the arrows specify which faces get glued to which other faces. So, for example, this front right face has 2 double arrows coming out of a vertex and a single arrow, and that then gets glued to that front right face there. So if you make those face identifications, you end up with a space which isn't quite a manifold. The 8 vertices of your tetrahedra get all identified to a single point, and that's a non-manifold point. It has a neighborhood which is a cone on a torus. So you just remove that point, and you end up with a manifold with toral ends, and that manifold, it turns out to be the complement of the figure-8 knot. So this topological description is one of the easiest ways of seeing the hyperbolic structure on this complement. Just as in the Seifert-Weber dodecahedral space, you take a hyperbolic polyhedron and make face identifications. Here you realize these 2 tetrahedra as hyperbolic tetrahedra and make face identifications. So actually you use ideal tetrahedra, so where the vertices are out at infinity on hyperbolic 3 space, and in fact you use 2 regular ideal tetrahedra, and you glue them up in the right way, and that gives you your hyperbolic structure. Okay, so I wanted to go through this in some detail because we're going to be coming back to this particular manifold again and again. So this is an example of just a hyperbolic structure on one knot complement, but one of Thurston's achievements was to prove his geometrisation conjecture for all knot complements, and has a very clean statement, so that let K be a knot in the 3-sphere, then the complement of K admits a hyperbolic structure if and only if K is not a torus knot or a satellite knot. So a torus knot is by definition a knot that can be drawn as a simple closed curve on a standardly embedded torus. And a satellite knot is one that can be drawn in a regular neighborhood of another knot, basically. Okay, so apart from these exceptions, every knot has a hyperbolic structure. So in some sense, almost every knot complement has a hyperbolic structure. It's another way of phrasing it. Okay, so the Dehn surgery problem specifies the interaction between Dehn surgery and hyperbolic structures. And as I said, there's a general theme that the manifold, if the manifold you start with has a certain geometric property, then that should remain true for most Dehn fillings upon it. Okay? So we know that most knot complements have a hyperbolic structure. So it should be the case that most knot complements Most manifolds you obtain by Dehn filling a knot complement should have a hyperbolic structure. And that's what the Dehn surgery problem seeks to quantify. So this, this phenomenon was established by Thurston in his hyperbolic Dehn surgery theorem. And what it says is that if you have a hyperbolic structure on the manifold M that you start with, and just for the sake of being definite, let's suppose it's just got a single toral boundary component, then for all slopes S on the boundary of M, with at most finitely many exceptions, the manifold that you get by Dehn filling is hyperbolic. And the slopes S for which the manifold is not hyperbolic are called exceptional. And the Dehn surgery problem asks how many exceptional slopes can there be. And this is a problem that's seen a lot of work on it, and I'm going to talk about sort of well, in some sense, a resolution to it. So it turns out that the worst case is given by the figure-8 knot. So that's the content of the problem. So the case of the figure-8 knot was analysed by Thurston, and he proved that the exterior of the figure-8 knot has precisely 10 exceptional slopes. So the way he proved this was he took his proof of his Dehn surgery theorem and applied it in this specific case, and he could see that outside this set of 10 slopes you could get a hyperbolic structure. And he could also show that for these 10 precise manifolds that they don't have a hyperbolic structure. So that gave that particular result. And so people took up this theme and explored various examples, and it seems that this was as bad as it could get. That 10 seemed to be the biggest number of exceptional slopes on a hyperbolic manifold. And this was then upgraded to a conjecture by Cameron Gordon, so that the conjecture is that for any hyperbolic 3 manifold M with boundary a single torus, M has at most 10 exceptional slopes. And, moreover, the figure-8 knot exterior is the unique manifold with precisely 10. And, as I say, this is what I and my co-author, Rob Meyerhoff, have proved, or at least we've proved the first half of that conjecture. We proved that 10 is indeed the maximal number of exceptional slopes. But we still don't know whether the figure-8 knot exterior is the worst case, is the unique example realizing that. Although there is some hope that when you'll see, I'm going to run through some ideas behind the proof, and you'll see that there is some hope of being able to prove the second half of the conjecture, because we'll see that the figure-8 knot and a few other manifolds come out in the proof as a separate set of examples that you have to analyze separately. That's good, because maybe for the rest you can do better than 10, and then it's only a question of checking a finite collection of examples after that. We can't do that yet. At the moment, we still don't know how to do that. Okay, so let me start off with, so this is what I'm going to be talking about today, and let me start off with some history to the problem. So as I say, it's received a lot of attention. Definitely, if you type in Dehn surgery into MathSciNet, you get loads of papers, and certainly at least 200 of them are related to this particular problem. And there have been some fairly high-profile ones of these. Here's a sort of list, far from complete. Apologies to people who should be on this list but aren't. Culler, Gordon, Lukey, and Shalem got a paper in the Annals on this. So did Boyer and Zhang. So did Hodgson and Kirchhoff. And there are many other papers along the way. So it's been a challenge, and there have been at least 3 different approaches to solving this problem, at least 3. So what I'm going to do is I'm going to explain some of the different approaches, and then we'll home in on the one that finally resolved it, which was the one that Rob and I developed, although that built on earlier work of others as well. Okay, so the first approach is to take Thurston's theorem, his hyperbolic Dehn surgery theorem, and just seek to quantify it. You just try and go through the proof and be very careful and hope that you can get an upper bound on the number of exceptional surgeries. This turns out to be very difficult, right? Essentially impossible if you try and do it in a completely naive way. Thurston's argument of his hyperbolic Dehn surgery theorem involved taking the hyperbolic structure on M and perturbing it a little bit, and from that creating hyperbolic structures on most of these filled-in manifolds. But it was a perturbation argument, and it's not clear how far you can perturb your hyperbolic structure before things go badly wrong. With a good deal of work, though, you can get some information, and so this was an approach taken by Hodgson and Kirchhoff, and they proved that there are at most 60 exceptional slopes. And what was striking about this was that this was the first universal upper bound, in other words, independent of the manifold M, on the number of exceptional slopes. Thurston's argument doesn't even give you if you try Thurston's original argument, you don't even get an upper bound which is independent of M. And this was the first such one. And they used the theory of cone manifolds and the deformations of them to great effect. But it was a hard argument, and it gave the number 60, which is a long way from 10. There's another approach which uses more topological methods, and so now we know the geometrisation conjecture to be true. We know precisely, in some sense, which manifolds have a hyperbolic structure. The theorem says that a closed orientable 3-manifold is hyperbolic if and only if it satisfies these 3 topological conditions. It's irreducible, atoroidal, and not cipher-fibered. So irreducible means that any embedded 2-sphere in the manifold bounds a 3-ball. Atoroidal means that you have no interesting tori, no pi1 injective embedded tori. And cipher-fibered means, cipher-fibered spaces are a very special class of 3-manifold which have very distinct properties. One way of defining them is that they are manifolds that are foliated by circles. But it's suffice it to say they're a very special class of manifold which is extremely well understood. So one way of proving this surgery theorem is to say, okay, how could a manifold that we get by Dehn filling not be hyperbolic? Well, there are 3 ways it could not be hyperbolic. It could be reducible, toroidal, or it could be cipher-fibered. So what people have done is they've aimed to bound the intersection number of slopes S1 and S2 where the filled-in manifolds are reducible or toroidal or cipher-fibered. And so there are 6 possibilities if you think about the possibilities for MS1 and MS2, and you can get very precise bounds in many cases. So, for example, Gordon and Lukey proved that if the manifolds that you get by Dehn filling are both reducible, then the 2 slopes S1 and S2 have intersection number 1. Just intersect once on the torus. And hence, the set of manifolds where that you get something reducible, that can arise for at most 3 slopes. Because if you have a set of curves on a torus, any 2 of which intersect just once, then there are at most 3 of them. So there's, as I say, a good deal of work being done this way on using this approach to the problem. However, when the manifolds are Seifert-fibered, things get difficult. You see, what can happen is, the way that the proof goes, for example, the reducible case, you have this essential two-sphere in one of the filled-in manifolds, and an essential two-sphere in the other filled-in manifold. You look at how those 2 spheres, how they intersect M. They intersect M in planar surfaces, and then you could look at the interaction of these planar surfaces. So you've got these surfaces which you can work with. And the combinatorics is very subtle and complicated, but with work you can get this sort of result. But Seifert fiber spaces don't have such a nice sort of certificate which certifies that they are Seifert fiber spaces. And so that's what makes things difficult there. So then there's a third approach to the Dehn surgery problem, which is in some sense between these 2 approaches. So the first approach tried to get a hyperbolic structure directly. The second approach tried to get a hyperbolic structure using topological methods. The third approach tries to get something in between, a negatively curved, so it uses geometric methods, but tries not to get a full hyperbolic structure, but just a negatively curved metric of variable negative curvature. And this is what Gromov and Thurston did a long time ago. They proved that for all slopes S on the boundary of M, with at most 48 exceptions, the manifold that you get by Dehn filling has a negatively curved Riemannian metric. And now we know, they didn't know at the time, but now we know that if a manifold admits a negatively curved Riemannian metric, 3 manifold, then it actually admits a hyperbolic structure. So I'm going to run through the proof of this because it's going to be important in the final proof resolution of the problem. So to really understand their theorem and where this number 48 comes from, you have to understand the geometry of the ends of the manifold well. So what does the end of a hyperbolic 3 manifold look like? So suppose I've got a 3 manifold M whose boundary is a non-empty collection of tori. And suppose I've got a hyperbolic structure on it. So what that means is I remove those tori and I realize that then as the quotient of hyperbolic 3 space by this group of isometries. So we remove the tori, and so that means that the manifold is now non-compact. It has ends which are of the form torus cross half-open interval. And these ends have a very specific geometric structure. Geometrically, they're obtained from the set of points in the upper half space model of hyperbolic 3 space with z coordinate greater than or equal to 1. And then you take that set of points above z greater than or equal to 1, and you then have a set of hyperbolic isometries which preserve that, an action of z cross z on that set acting by parabolic isometries. So the parabolic isometries just act by Euclidean translations. So a fundamental domain for that action is given by this a parallelogram in the plane cross half-open interval going off up to infinity. So the ends, the torus cross I, are obtained by taking parallelogram cross I and identifying opposite sides in pairs. So that's what the ends of a hyperbolic manifold look like, and it's called a horrible neighborhood of the end. Because this subset of hyperbolic space consisting of points where z coordinate is greater than or equal to 1 is a horrible. Okay, so let me just give an example on the figure 8 knot. So the figure 8 knot we realized as two ideal tetrahedra with their faces glued. And here's the boundary in grey of a neighbourhood of the end. So you can see you've got these chunks of the manifold which are triangle cross half open interval, and you glue those together and they form parallelogram cross half open interval. So in hyperbolic space, the inverse image of these ends, well, what does it look like? Well, going back a slide, we know that one component of the inverse image looks like this horrible z greater than or equal to 1. But there are other components which differ from that by a covering transformation. So you get other horribles, and what they look like is there are lots of them dotted around in hyperbolic space. So there's z greater than or equal to 1, and then there are covering translates of it, which are these balls here. And there are lots of them. I can only draw so many. They get smaller and smaller, and they're dotted around all over the place. In fact, actually, I can give you a good picture of this. If I take this picture and I pick it up and put it on its side and look underneath, then I'll be able to see lots and lots of horribles, and I get a picture that looks like that. Sorry?
If you draw maximal horribles.
These are maximal horribles. Sorry?
Are these maximal horribles?
No, not yet. They are in this picture, but I haven't defined maximal yet. So this is a picture created by Moore and Thistlethwaite, and this is the horrible arrangement that you get in the case of the figure 8 knot complement. So this is looking at hyperbolic space from underneath. Okay, so here's another picture. If instead of looking at it from underneath, I look at it from above, so just going back a couple of slides, if I look at this picture from above, I'll see these balls in the plane. Some might cover others, they'll be of different sizes, and here's a picture of such an arrangement of horribles looking from above. So this is actually not the case of the figure 8 knot. This is the case of the Borromean rings complement. They're the Borromean rings, and the complement of them emits a hyperbolic structure. And so it's got a manifold with 3 ends. So looking from one end at all the arrangement of horribles, you get a picture like this. So this actually was created by a very beautiful computer program and powerful called Snappy that was created by Jeff Weeks. And it really is amazing. What you can do is you just take your mouse and you draw a picture of a link or not, and it'll just, if it's got a hyperbolic structure on its complement, it'll find it for you. It's not guaranteed to, but in practice it does. And then from that you can find out all sorts of nice geometric data about relating to the manifold. So for example, you can get pictures of these horrible diagrams. Okay, so the key to the Gromov-Thurston proof was this notion of slope length. If you now take a maximal horrible neighborhood of the end. So these horrible neighborhoods of the end, they come in one parameter families, because instead of taking z greater than or equal to 1, I could have taken z greater than or equal to 2, for example, and shrunk the horribles. But imagine doing the opposite. Imagine trying to expand these horribles and expanding and expanding and expanding until they just touch. And at some point, they'll just stop. That's a maximal horrible neighborhood, and the boundary of that is a Euclidean torus. The torus inherits this Euclidean structure because it's a quotient of z equals 1 by translations. And each slope s on that torus is realized by a geodesic in this Euclidean structure, and the length of the slope is by definition the length of that geodesic. So you can visualize this slope length as translation length. So each slope element gives you an element of the fundamental group, and so a covering transformation which acts via Euclidean translation taking one point on the plane to another point on the plane. And the length of that translation is the slope length. And Gromov and Thurston proved their so-called 2 pi theorem. They proved that if the slope length is more than 2 pi, then the manifold that you get admits this negatively curved Riemannian metric. And the proof is very clever, but it's surprisingly straightforward. What you do is you just take your manifold, you remove a horrible neighborhood of its ends, and then you just glue in a negatively curved metric which patches up near the boundary. And you can do that as long as, they show that you can do that as long as the slope length is greater than 2 pi. So to bound the number of exceptional slopes, all we need is the result of Gromov and Thurston that says that there are at most 48 slopes with length less than or equal to 2 pi. That's how they get the number 48 from. So I want to explain the proof of this now. How do you get that number 48? Well,
Sorry, can you go back to the slope length definition?
Slope length definition, there it is.
Just on the Euclidean tori.
Yeah.
For maximum horrible.
Yeah. So each slope has length at least 1. This is this very nice little lemma of Thurston. How do you prove that? Well, you let n tilde be the inverse image of n in hyperbolic space. And as we arrange that one component of this is z greater than or equal to 1. There are other horribles around, and there must be one that bumps into this z greater than or equal to 1. Otherwise, we could have expanded the horrible neighborhood a little bit further. So there's a horrible that just touches this. Now, the covering transformations take the interior of this horrible to the interior of another horrible, and the interiors are all disjoint. So that means that this horrible has to get translated to here, and therefore has to be moved at least distance 1, Euclidean distance 1, otherwise the interiors of those two horribles would intersect. Okay, so now it should be clear why there's a universal bound on the number of slopes. We've got this Euclidean torus. This universal cover is just the Euclidean plane. We've stuck a dot on that and then looked at all of the actions of the images of that dot under the Euclidean translations. And the distance between any two dots is at least 1, because every slope has length at least 1. And what we care about is the number of slopes with length at most 2 pi, in other words, within this disk. So if you just think about it, you're just wiggling around in this, there's a parameter space of lattices in the plane, and the constraint that the slope length is at least, every slope length is at least 1, forces the number of slopes to be of length less than 2 pi to be universally bounded. It's kind of obvious. But how do you actually quantify this? How do you get the number 48? Well, originally it was quite a complicated argument, but now there's a much more streamlined version. Using intersection numbers. So let delta of S1 and S2 be the intersection number, the modulus of the intersection number between two slopes. And there's a little lemma that says that this intersection number is at most the length of slope S1 times the length of slope S2 divided by the area of the torus. And here's the proof of it. So here's S1. It's a geodesic in the plane. Here's S2. It's another geodesic in the plane. They span a parallelogram. Now that area, the area of that parallelogram is equal to the area of the torus multiplied by the intersection number of the slopes. Okay, so that's rearranging this formula is equivalent to that the area of the torus times the intersection number is less than or equal to the length of S1 times the length of S2. But the area of the torus times the intersection number is the area of this parallelogram spanned by S1 and S2. And clearly, the area of a parallelogram spanned by S1 and S2 is at most the product of their lengths. So that gives you that. So putting that into our case, we get that the intersection number between two exceptional slopes is at most 2 pi squared, because that's 2 pi is the upper bound on the length, divided by the minimal area of a torus. And if you have the minimal possible area of the torus is √3/2, given by the hexagonal packing of these dots, all with neighbouring ones having distance 1. So that gives you the intersection number between two slopes is at most, two exceptional slopes is at most 46. Plug in that calculation. And then that 46 gets to our 48 via a very nice lemma of Ian Agol, which says the following, that if we have let S be a collection of slopes on the torus, such that any two slopes in that collection have intersection number at most delta. Let P be any prime more than delta, then the number of elements in the number of slopes that we're dealing with is at most P plus 1. And the reason is you just take your slopes, which are just elements of Z cross Z, and you just reduce mod P. You then get elements of ZP cross ZP. Those are different elements of ZP cross ZP because the intersection number between any of them is less than P. They were co-prime before, so you actually get different elements of the curve over the projective line over FP. So you get the number of slopes is at most the number of elements in that projective line, which is P plus 1. Okay, so it's a very nice argument. Setting P to be the prime 47 gives you then that there are at most 48 exceptional slopes. Okay, so that's a quick summary of the 2 pi theorem. And how are we going to improve that bound? How are we going to get from 48 down to 10 using this method? So the key is this inequality here, that if you want to bound the number of slopes, one way of doing it is to bound that intersection number. And one way of bounding the intersection number is to say that it's at most the slope length of each one divided by the area. So one way of improving the bound on the intersection number is to increase the lower bound on area. Currently, √3/2 coming from the hexagonal packing. Or to decrease the critical slope length below 2 pi. Both of those would help, and we do both of those. So first of all, the known lower bounds on area have got better and better with time. Colin Adams proved that improved by a factor of 2 to get that the area was at least 1.73. Cao and Meyerhoff got that the area was at least 3.35. And I'm going to come back to their proof in a bit. And Gabai, Meyerhoff, and Milley proved that the area was they didn't actually write this down, but Rob Meyerhoff told me that that's what they did, that the area was at least 3.7 under some hypotheses, which we'll come to as well. So that dramatically improves the lower bound on area, and hence it seriously improves our known upper bound on intersection numbers. But first, what I want to do is I want to show you how you can improve the lower bound, improve the critical slope length below 2 pi. So here's an alternative proof of, here's an improvement which gives you that the critical slope length is actually 6, is at most 6. So it says that if the slope length is more than 6, then the manifold MS is irreducible, atoroidal, not cipher-fibered, and has infinite word hyperbolic fundamental group. And then this was proved by myself and Ian Agol about 13 or 14 years ago now. And then, as a consequence of Perelman's work, we then know that the manifold is actually hyperbolic. So this reduces down from 2 pi to 6, which seems like a small improvement, but it turns out to be crucial. So I want to give a proof of this now, or at least some parts of it. So suppose that the manifold that we get by Dehn filling doesn't satisfy one of these, all of these conditions. Let's just for the sake of being definite suppose that it's reducible. So in other words, it contains a two-sphere that doesn't bound a ball. That two-sphere we'll call S. So this two-sphere is living inside the filled-in manifold. And in the filled-in manifold, there are these solid tori which we attached. They're by Dehn filling. So you look at each core of each solid torus, which is just a simple closed curve, and you make those simple closed curves intersect the sphere transversely. And then what that means is that they then intersect the solid tori in a collection of meridian disks. Then what that means is that in M, the intersection with the original manifold M, the sphere intersect M is then a planar surface, because it's a subset of the sphere, and its boundary components each have slope S. With a bit of pushing and pulling, which is very standard in three-manifold theory, you can actually make sure that this planar surface P is what's called essential, which means, in this context, that it's pi1 injective and a boundary version of pi1 injectivity. And the reason for making it pi1 injective is because then you can then realize the planar surface P as a minimal surface in M, your original hyperbolic manifold. It's a general existence result. So P is now a minimal surface sitting inside our original hyperbolic manifold with boundary slopes S. Okay, so if you have a minimal surface in a Riemannian manifold, it inherits a Riemannian metric. And the intrinsic curvature of that metric is always, at most, the ambient curvature of the manifold. That's some basic Riemannian geometry. So if we call that intrinsic curvature kappa, then kappa is at most -1, because the curvature of hyperbolic space is -1. So, applying Gauss-Bonnet, we get that 2 pi times the Euler characteristic of our planar surface P is equal to the integral of its curvature over P, which is less than or equal to the integral of -1 over P, which is just minus the area of P. So in other words, rearranging, we get an upper bound on the area of our planar surface. It's at most 2 pi times by minus the Euler characteristic, in other words, the number of boundary components -2. So the key now is to show that if we can show that each boundary component of P contributes at least 2 pi to the area of P, we'll have a contradiction. Because then we'll have area at least 2 pi times the number of boundary components. So what you do is you now look at the nature of the ends of this manifold and you look at how the surface sits inside those ends. So you get a sort of picture a bit like this, a little bit like that anyway. So here's z greater or equal to 1, and here's a portion of the surface sitting inside there. And so the idea is think of this as a lift of our slope S cross I, cross half open interval. It turns out that the area then in there of that bit of surface is at least the slope length. It's not so surprising. And so that means that each boundary component of our planar surface contributes at least the slope length of S to the area of P. So if the slope length is more than 2 pi, we've got a contradiction. That's not quite good enough, because what we want to show is if the slope length is more than 6, we have a contradiction. But the advantage of this method is you can see that what we haven't done is we haven't utilized all of the area that's possible. We've only considered the bits of the surface living inside the ends. There's other stuff as well. Looking back at the case of the figure 8 knot, the ends sort of look like this, the light grey, but there's stuff which is missed out. And if you take account of the area of the surface in the bits that missed out, you get an improvement. And you actually get that each boundary component of P contributes at least 2 pi over 6 times the length of S. So that gives you an improvement of our slope length by that factor. And it shows you that if the slope length is more than 6, then the manifold is, we get a contradiction, and hence our original, we deduce that it must have been irreducible. And other conclusions follow as well, atoridality, etc., proved using similar sets of techniques. Okay, so that's a very brief history of the sixth theorem, as it's now called. And how much longer have I got? I've got 5. Okay, I did definitely start late though. Anyway, so we'll carry on. Okay, so how do we, this around as well, 12 or so years ago, got us down to at most 12 exceptional slopes. So improving the lower bounds on the area of the boundary torus and improving upper bounds on the length of exceptional slopes from 2 pi down to 6 gave us at most 12 exceptional slopes. And that's where the story was up until, let's say, fairly recently. The problem is it looks like getting down from 12 to 10 shouldn't be that hard, right? But it is. So there's an obstruction. And the obstruction was observed by Ian Agol. The problem is he gave an example of a manifold M with the following 2 properties. It has an exceptional slope S with length 6. So it means you can't do any better than 6. 6 is as good as it gets. And it has 12 slopes with length at most 6. And so if you're just using slope length, it looks like you cannot get better than 12. This was an example of the horrible packing in the cusp tor, looking from infinity, and the dots correspond to bad slopes. Anyway, this picture plundered from his paper. Okay, so that was a serious problem. But fortunately, we know now that this example falls into a well-understood family of exceptions, which we can analyze separately. And this is as a consequence of work of Gabai, Meyerhoff, and Milley. So, as I said, they proved that the cusp area of M is at least 3.7. It was this improvement. Unless M is obtained by Dehn filling, unless M itself is obtained by Dehn filling something else, one of a finite list of manifolds. So here's a list of 8, 9 manifolds from the census of hyperbolic 3 manifolds. So these have been well studied. And fortunately, Agol's example falls into this family of exceptions. So there's a hope that you can separate that off, analyze those guys separately, and prove the theorem for the remainder, for everything else. And that's exactly what we did. So using this lower bound on area and the sixth theorem, you get from 12 to 11. Right, so that's getting really close. Each time you want to improve this, it really is it's much harder. So just taking their theorem alone and just plugging it in doesn't give you enough. What you have to do is you have to go back and adapt their methods. So their methods. So we're running a little bit out of time, so I'll be fairly fast. So what did they do? So there's this work of Cao and Meyerhoff. How do they get their lower bound on area? This was the lower bound that was used 12 or so years ago. They looked at a certain number, E2, which is related to the size of the second largest horrible. And the point is that if E2 is close to 1, then the second largest horrible is basically as much the same size as the biggest horrible. So the lower bounds on area that we get by looking down at and seeing where the largest horribles are, they contribute area to the cusp torus, you get the same contributions from the second largest one. So you improve your area on cusp torus by at least 2, which is great. So E2 is close to 1, we're happy. If E2 is very far from 1, that means that these little second largest horribles are really, really small. And you think that can't help at all. But what that means is that turns out to force the largest horribles to be extremely well separated. And hence we get a good lower bound as well. So if E2 is really close to 1, we're happy. If E2 is really large, we're happy. And in between, we have to get a computer to analyze over parameter space. You just analyze over possibilities for E2, you get a lower bound for each, and eventually you get the area is at least 3.35. This computer calculation is done rigorously. It's not, they take account of round-off errors and all sorts of other things. And we had to do the same when we did ours. Okay, so then Gabai, Meyerhoff, and Milley took this technology and they really hit it hard by looking at the second, third, and fourth largest horribles. So you have E2, E3, and E4. They examined that parameter space. And as I said, they deduced that the area was at least 3.7 unless certain configurations of horribles arise. And in those cases, you deduce that actually the manifold is obtained from this family of exceptions. So that's how their theorem worked. So what we have to do is, so what do we do to prove this, to get down to 10? Well, we do improve the sixth theorem. We improve the sixth theorem. You can't get better than 6 to just some number, but you improve it by getting a function of E2. The point is that as E2 gets larger, the second largest horribles are getting further away, and so we get more area above them. And the area calculation was what was needed to prove the sixth theorem. So you get a formula which says that if the slope length is at least this or this, then the manifold is hyperbolic. So here's a picture of the critical slope length as a function of E2. And you can see that when E2 is 1, when the second largest horribles are as big as the largest horribles, the critical slope length was 6. And you can't do anything about that. But as E2 gets bigger and the second largest horribles get smaller, critical slope length goes down and down and down and down, and that acts in our favor. And so what you have to do is to say you have to repeat the analysis of what Gabai, Meyerhoff, and Milley did. But this time specifically, they were interested in finding lower bounds on volumes of manifolds. Here you search specifically for the number of slopes length less than this critical slope length. And it turns out that that alone doesn't do, so you have to introduce more geometric obstructions. So there are certain horrible configurations which can't arise, and so on and so forth. And you run over a 6-dimensional parameter space. You get your computer to chug away over a 6-dimensional parameter space. Computer calculation takes about 2 days. You can't do it by hand, in other words, it's not so outrageous. And it just works. There are cases where you have to make sure that something is less than the critical slope length, and it is only just by about 0.0001. So you really have to. It's very, very close indeed. And at that stage, your computer is really chugging away, working very hard, because the way it works is, how do you get a computer to do this? Well, you divide your parameter space up into little chunks, and you, instead of dealing with real numbers, you say, actually, I'm dealing with a number between this bound and this bound. And then you do all your calculations using an interval arithmetic. And so when you want to show one thing is bigger than another, you have to use very, very little chunks, otherwise things go wrong. And that's why the computer takes such a long time. And it just works. And the final thing, I know I've gone over time, but can we trust this? The answer is yes. I mean, I would say that, wouldn't I? But your computer code is very straightforward. You can check it by hand, just like a proof. It reads, it's just sort of geometric calculations, like the area of a triangle is this function as a function of the sides, that sort of thing. And as I say, you can control round-off errors, potential errors coming from the fact that you're using floating point arithmetic. And You also at some point had to use SNAP-E as well, but you use a version of SNAP-E which uses exact arithmetic, where the numbers are algebraic numbers that it deals with. So yes, you can trust the computer, and that proves the theorem. So I'll leave it there.